All right, so first quiz, again, don't worry too much about this. We'll have lots of quizzes. We'll drop lots of quizzes. We will, more importantly, use this to see where you still need to do a little bit of work before the exam next week, which is more important. So, so let's go through this. First, some Lewis structures. First, we have nitroethane, which is CH3CH2NO2. We did a similar problem to this in one of those worksheets, or it was at the bottom of one of those worksheets. These are drawn as condensed structures. I didn't put any kind of traditional Lewis structure-y type Lewis structures with unusual elements like you'd get in Gen Chem, because I just don't think that's a big part of what we need to do in this class. So we're going to see a lot more stuff like this. The tricky part of this is that NO2 at the end, so we have to figure out what to do with that. So hopefully you got that a Lewis structure for the rest of it would look something like this. And then just like any other Lewis structure, you start with the connections. So you've got N, and then we've got O and O, or if you did it at an angle, or one up and one down, however you want to do that. Remember, in a Lewis structure, it doesn't matter. So we'll start with that. And then we say, do we have enough electrons here? No, so we're going to add in the rest of our electrons, which ends up coming out, if you start going around, something like this. 8, 10, 12. So that is the appropriate number of electrons. Are we done then? What's wrong here? We need formal charges. What else is wrong? Yeah, the nitrogen's short 2 electrons, right? There are only 6 electrons around this nitrogen, 2, 4, 6, and it needs an octet. So what are we going to do about that? Right, we're going to have to turn one of these bonds into a double bond, so we'll take out a pair of electrons and go like that. Now we can evaluate formal charge, which comes out to a positive on this nitrogen and a negative on this oxygen. And that's nitroethane. Questions about that one? Okay, going on to a pseudo nitrile, which was one that we looked at. Also, same idea here. We start with this, and then when we add our additional electrons, we can go no, wait, that's not right. Like that is the right number of electrons, I believe. So, what does that get us? Is that right? Right, so same deal, not enough on carbon, so we have to take some of these electrons that we had on the nitrogen, share them with the carbon, and this ends up being a triple bond. So we share 3 pairs of electrons. And evaluate formal charges. We find that all the formal charges here are neutral. So we're good. So far, so good. Okay, let's move on to the line structures and the names. All right, so let me see if I can write this whole thing up here. Make sure it's the same thing. Acetonitrite. It's a solvent. It's a common solvent that I'm not sure if we'll use it in this class. Maybe. Okay, there's our first line structure. So a bit of a mess here. Well, not a mess, but you know, it's a big thing. So how did you go about figuring out how to draw this as a line structure? Sure. Okay, so you did it as a Lewis structure first, and then made the connections accordingly. Okay, let's do that, and I'm going to actually take it one step further and not even draw in the hydrogens, because we know we're not going to have the hydrogens in the line structure, right? So let's try that. So we just go Make sure everything's connected in the right way. I think that's right, right? Okay, and then in either form, then I think it's always easiest or works well to look for the longest chain, because we got to do that to name it anyway. So let's try to find that first, and then that'll help us draw it. So what's the longest chain here? Yeah, it's 8. If you start up here and you go like that, you find 8 in a row. Okay. And then if we number that, we got 1, 2, 3, 4. So that way what we can do is draw a line structure of 8 in a row and then go from there. So we can go 1, 2, 3, 4, 5, 6, 7, 8. Number those. 1, 2, 3. Just to make sure that we've actually done it properly. And then we can say, all right, let's look at those substituents. We've got a 1 carbon group coming off of number 3 and 2 1 carbon groups coming off of number 4. And that's it, right? Maybe see anything else here? You could not do it that way. You could just leave it in this format, and you could draw it like you see here. So you could say, all right, I see 4 across the top, like that, and that's going to connect to 1, 2, 3, 4, 5, 6 down here. So 1, 2, 3, 4, 5, 6. And then I got to get 1 more carbon off there like that. That's fine. That's a totally appropriate line structure as well. Nothing wrong with that. This one makes it a little bit more clear what the main chain is and where the substituents are, but there's nothing wrong with this for this kind of a question. So if you just left it in that form and did it this way, that's okay too. Did anybody have a different technique that seemed to work or maybe work? Okay. All right, so then the naming comes in. So we know it's got 8 carbons in our chain here. So that gives us an octane. What are the substituents then? Right, we're going to have methyl groups on 3 and 4. Right. 3, 4, 4. Trimethyl octane. All right, 1 number for each substituent, and they're all methyl groups, so overall it's trimethyl. Is that what you got? Maybe? Nobody wants to admit it? Just poker faces. That's fine. All right, let's move on to the next one. Okay, I think I got them all there. So how would you do a line structure of one like this? Yeah, you recognize that there are 6 carbons connected in a ring like that. So that's probably where you want to start with the line structure. We could do it the same way, but we know our main chain is going to be these 6 in a ring. So we can go like that. And then we should keep all the substituents kind of in the same positions so we don't get confused. We could draw them wherever, but we got to make sure they have the same relationship to each other. So we're going to go here, here, and here. And that one has 2 carbons, so we got to put one more on there. Does that look right? Okay. All right, I think that's good. Okay, so now we're going to name it. As you said, we're going to end this name with cyclohexane. And I think the trickiest part of this one is how we're going to number it. Because remember, you can start anywhere on a ring with the numbering. But you've got to figure out where you're going to number, where you're going to start, and which direction you're going to go so that the substituents all have the lowest possible numbers. But what do you think the best choice is for that? Start where? Start at the top. So call this one 1. And go, where are you going from there? Like this? Okay. Anybody find a better one? Start down here? Okay. So 1, 2, 3. I should use a different color. This is confusing. Okay. So the first way gives us substituents at 1, 3, and 4. The second way gives us 1, 2, and 4. So what's better? The second way, the 1, 2, and 4, because those are going to be lower numbers overall. So we'll stick with that numbering scheme. All right. Yeah. Yeah. It's worth a point out of 2, but it's wrong. Yeah. Okay, let me move this out of the way a little bit so I have some room. Okay. That means that we're going to have an ethyl at 1. That's here. And then methyl groups at 2 and 4. So that's going to be 1 ethyl, 2, 4 dimethyl cyclohexane. Yeah? All right. So that was the first quiz. Congratulations. You do when there are multiple substituents like that. I'll allow it for this one, but for this quiz. That's right. When there's only one substituent, it's assumed as 1. But when there's multiple ones, you want to specify that. Yeah, I agree, but that's not the rule. Sorry. I think you have a good point, but that's yeah. The better answer or the better choice, I guess, is to just always use the numbers. Yeah. You can always put the numbers. It's always okay to put the numbers in. Right. So. Sure. Yeah, agreed. Did you have another question? Anybody? Okay. Well, let's move on. So first quiz, like I said, probably going to be a little whatever. But the exam's coming up next week, so we'll have lots more practice in here doing these names today, or a little more practice anyway. But please get into the problems at the back of the book. Go through all those. It's really a practice thing. It's doing it over and over again and trying to get it right on your own. That's going to prepare you the best for the exam. All right, so everybody grab models. Oh.
Are there other places we can find practice problems?
Sure.
And a lot of them are like over complicated from what we've been doing. And like the ones in the book, not every single one has an answer.
Okay.
And some of them were stuff.
Yeah. Yeah, I have all kinds of stuff. Let me find that and I'll give it to everybody. What? Why? Because we skip it today. Because the exam's on Wednesday.
Oh, like, did you talk about this week at all?
Yeah.
What did you say?
Just that. We didn't have class on Monday, so we're going to do class today because the exam's on next Wednesday. And so otherwise it would be not enough time between the class and the exam. So, all right, so take out your models, and the first thing we're going to do is just take two of the carbons, two of the black ones, and connect them together with a bond of your choosing. And then add some other bonds in there, just so all the holes are filled up. So it's kind of like an ethane molecule, like CH2. Everybody got your ethane? Yeah. So you'll notice, and I know we've mentioned this briefly, but you'll notice that the bonds can rotate, like you said. And that's done purposely. They could have made these things square pegs or something. They made them round because they're supposed to be able to rotate. So if you look directly down your bond so that the two carbons are right on top of each other, or right in line with one another, just kind of hold it in front of you and look like this. You'll notice that there are basically two extreme positions that you can rotate it in. There's the one where all the hydrogens are lined up with each other, essentially blocking one another. Sorry, I'll wait for you guys to get your sets late.
My set was just a complete class.
Oh, you had to organize it first? Yeah. Those previous classes, they just have no respect. Putting these things back in just whatever condition. All right, we got them. You don't need the balls, you can just go with sticks. All right. So if you have your models, just look down that bond, that carbon-carbon bond, and kind of start turning it around and noticing those different positions that can be. With the hydrogens either being between each other or right on top of each other and right in line. Yeah, it's not going to work if you don't put the other sticks in. Okay. That's fine. So there's actually names for these two positions. I'm not writing anything down here because this is not something that is going to be on the exam, but it is going to become important for the next part thing that we're going to do. The one where they're all lined up with each other, so like this, that is called an eclipsed conformation. So I will write a couple definitions here. We're not going to go through the whole how to draw this, but I'm going to write a couple definitions. So first, this idea of conformations. We call different conformations of molecules different states of rotation around bonds. So this would be the simplest example of that. You just rotate this little molecule and you can get two different conformations. You can get the one where they're lined up and the one where they're not lined up, and then the stuff in the middle. As we get into bigger molecules, they will have more possible conformations, more ways that they can be rotated. And we're going to look at two states of this. So we're going to have the eclipsed conformation which we say is lined up. And this is the higher energy conformation. We'll talk about why that is in a second. And then the other extreme, where they're not lined up, where they're splitting each other, is called staggered. And this is generally lower energy. Why do you think that is? First, let's remember, what does it mean for something to be higher or lower energy? We're talking about stability. What's more stable? Lower energy or higher energy? Lower. So what we're saying here is that the staggered conformation, where they're split like this, is more stable than the higher energy, than the eclipse when they're lined up. Why do you think that is? Right. Now, in this particular example of ethane, it's actually a little bit more complicated reason, but for almost every other case, it's because they're not interfering with each other. So to demonstrate that, let's build let's build a larger molecule. Let's build butane. So put 4 carbons in a row, and then fill those hydrogens on those end ones. Remember, you already have 2 in a row, so if you want 4, that means 2 more. So you all got that. Start from scratch. Oh. So some of them have little pieces broken off in the holes.
The 3 carbons, right?
4. 4. Let's do 4. So we'll add 2 more carbons. And now you can imagine these things kind of twisting and spinning around, and there are many more possible conformations, many more possible ways to spin them around. We're going to look at a couple in particular. So let's look first at the conformation as you get your pieces together. Well, while you're getting your pieces together, just start spinning them around, start playing with it, and see if you can find what you would expect to be the highest and lowest energy conformations of this molecule. Just based on kind of what we talked about, the idea of these things interfering with each other, what would be the worst, least stable position for these things to be in? And then what would be the most stable position for these things to be in? If you're still building, that's fine. A couple minutes to work on that. Do you think you got an idea? What do you think would be the least stable or highest energy conformation? What you got right there? Anybody else? So y'all came up with roughly the same thing. You got the opposite.
What?
I'm going to call that the most stable.
Yeah.
Yeah.
Oh, we're doing that.
Yeah, that's right.
Oh, sorry.
That's what I figured. So yeah, so just knowing that and looking at the models, you're able to come up with that the eclipsed conformation, where those 2 CH3s are right in line with each other, that's going to be the highest energy, because you can really see, if you imagine, in reality, these are these big spheres of electron density. If you imagine, those things are really going to get in each other's way there. So that's going to be much higher energy. And then the lowest energy, or the most stable, is going to be if you flip that thing all the way around and it's totally staggered, which is just like how we draw these things, right? They're all staggered, everything's splitting everything else. So we have these ideas that the bonds will rotate to kind of settle in the more stable conformation. Now, room temperature, there's actually plenty of energy, so these things are just flipping around completely. But as we cool down and get lower and lower in temperature, eventually we get to the point where there's not enough energy anymore, and they'll settle on the more stable conformation. The book in section 3.6 goes through all this and talks about drawing these things called Newman projections, which are ways to draw and look at this. We're not going to get into that this semester, so we're gonna skip that part a little bit. We are going to talk about this idea of conformations with a slightly larger molecule, and that is cyclohexane. Sorry if I'm a little hoarse. I was sick. I probably would have canceled class on Monday anyway, even if we had the snow. But I think I'm getting over it. But I can feel my throat like sort of closing up. So we'll see how well we do today with all that shoveling. I should do more of the exercising. Anybody here do exercising? Seems like that's a good idea. You shouldn't just go out and shovel a bunch of snow. Oh well. Okay, so let's see what happens when we go up to 6 carbons here. Let's think a little bit about bond angles before we do that. So hold on to your models. And let's title this. Okay, and let's think about those cycloalkanes. This is our smallest cycloalkane,
Propane.
Yes, cyclopropane. We'll just call it cyclopropane for now. What are the bond angles in cyclopropane? Anybody remember 10th grade geometry or whatever? What's the inside angle of a triangle? 60. Yes, 60. Very good. You have an equilateral triangle, 60-degree angles. What is the ideal angle for a tetrahedral bond, for carbon with 4 bonds? sp2e. Yeah, 109, 110. They're that range. So that's pretty far off, right? That's way different from 60. In fact, if you try to build cyclopropane with these models, you will break them, which is probably why they're a little bit snapped off in all of these things. Because if you imagine, if you take 3 of them, you can feel that strain of trying to push those things together and push them into the 60-degree angles. It's just not going to happen. Actually, if you do want to make it, you have to use the curvy ones to kind of help it around. The what? Oh yeah, and you can use the gray ones too. Yeah, that's right. Those are the ones that have the extra holes, right? So you can feel that strain. And because of that, cyclopropanes are somewhat reactive. Those types of things can open up and do great reactions. So let's move up then to cyclo butane. What's that angle? 90. Good. It's a square. I know I said there wasn't going to be much math here, but come on, you should know the angle of a square, right? So then, oops. Whoops. So if we go up to a pentane, I didn't even know this one, so I have to look this one up because I never remember it. Anybody remember this one? It's about 108. And then cyclohexane, a hexagon, what's that angle? That's another nice even one. Yeah, that's 120. Okay. So based on this, what should be the most stable ring? Which angle is the closest to the actual observed angle? Or the actual, which angle here is closest to what we want in tetrahedron? The 108. And it's true, cyclopentanes are fairly stable. However, cyclohexane is actually the most stable. It's the most common ring. You see it in everything from sugars to starches to things like hormones. Pretty much any chemical that's important in the body is going to have something of that shape in it. Incredibly important, but yet its bond angle is pretty different. And in fact, if you build, so let's do this now, try to find 6 good black ones. And if you can, try to use all the same color for at least the bonds that connect the carbon atoms. It doesn't matter what colors you use for the ones coming off of it. Let's try to build a 6-membered ring, so cyclohexane, with the same color bonds, or the same length at least. I don't care about the color, but the same length bonds between.
Oh, yeah.
I don't know how your building is going, but you'll notice if you try to put this thing into a flat 6-membered ring, you again kind of feel that strain, right? It doesn't quite work. It wants to flip itself around a little bit. And that's kind of gets to what we're going to talk about here. So I'm going to finish my model. I'll give you some time for yours. So get 6 carbons together in a ring, and then try to get as many of the hydrogens on there as you can. Don't have to get all of them necessarily. But at least try to get a couple of carbons worth of hydrogens attached. Yep, 6 carbons in a row, or in a ring. Right. So you've all noticed that now. It doesn't want to line up. It doesn't want to be flat. It wants to flip, and the way that it flips, you'll notice, is kind of to make it in that staggered arrangement, like you said, like we've just been talking about. It doesn't want to be lined up. It wants to be staggered, and we can feel that in the bond angles. And in fact, when cyclohexane takes on this staggered kind of conformation, it actually does get those bond angles almost exactly to 110. So it's really, or 109, in between 109 and 110. So it's just where it wants to be, and that's why that is such a common conformation. So we're going to practice actually drawing these and understanding how they work and how they change conformation. So you remember when we did conformations with the ethane or the butane, it was just a matter of kind of spinning a thing around. Now we have a bunch of bonds working together, so you kind of hold 2 ends, and to flip the conformations, you have to flip the ends kind of like this. And you'll notice all the bonds rotate when you do that. You can kind of flip it back and forth. Well, don't push that hard. Just let them rotate. Try not to put strain on them. And you should be able to get them to kind of flip back and forth like that. Yeah. Oh, you got this connection.
Yeah.
Sorry.
I didn't.
Try the other side if you want.
That's okay, because then I have to try to build this again.
Okay.
I mean, I could do it a little bit.
Oh, we don't talk about how to decide. So. Okay, I did something.
All right, so we're going to look at these conformations of cyclohexane and how we can express this unusual geometry. Does anybody have a book with them? If you do, you might want to get this out just to have something to look at. If you don't, it's fine. We're going to go through it together. But if you look at page 80, if you have the same edition, or close enough, yeah, it's in chapter 3. They have this thing of how to draw these chair conformations. So we're going to go through that and talk about how that works. But if you want a picture right next to you to help you do that. So we have to draw this in such a way that it's clear what we're drawing. It's clear which part is where and what's pointing up and what's pointing down. So to do that, let's first make sure we all have really good models. The way we're going to have the good model, or the correct model, it should look something like this. If you look at it from the side, from straight onto the side, you should see two sets of parallel lines in the middle from those two bonds. And then you should see one end kind of pointing up and one end pointing down. All right? This is called a chair conformation. It kind of looks like a chair, a weird sort of chair, but that's what they're called, where the parallel lines are like the seat, and then there's kind of a footrest and then a headrest coming up. Yeah. Another way to find it is you should have 3 hydrogens pointing straight down, vertical straight down, and then 3 pointing straight vertical up on the other carbons. Every bond should be perfectly staggered, meaning if you look straight down it, you see a hydrogen splitting 2 other hydrogens. All right, I see some good ones. I'm going to come around and make sure everybody's got a good one to start with. So yours is a little bit tricky because this bond is short. Yeah. It should kind of stand up on its 3 legs when you got it in the right spot. Okay, this is close. You want to get those things parallel in the middle. Just like that. 3 little legs. See if you can get 3 legs in the middle. Or not in the middle, 3 legs alternating on each side. Yep. Yeah. Do that. 3 legs. You had it. I saw you had it. But yeah. They should be alternating carbons. So everything's kind of going up, down, around the ring. Staggered the whole way. Yep, you got it.
Oh.
Yep, good. That's good. Yep. Okay, can we look at that? So you see how there's kind of this up, down, alternating around the ring? Let's look at a couple things about this before we try to draw it. So first, you'll notice that each carbon has one bond, one hydrogen bond, that's either going straight down or straight up, and then one that's kind of going off to the side at an angle, pointing out of the ring. Can you see that? So a straight up or straight down, and one kind of going out. We'll give those names in a little bit. You'll also notice that the straight up or straight down alternates. So it goes up, down, carbon to carbon. Right? Okay? And you'll notice that the outside ones also alternate. So they kind of go out at an angle up, and then out at an angle down, and then out at an angle up, and out at an angle down as you keep coming around. And then here's the part that's going to help us draw things. This entire structure that you have now, including the hydrogens and everything, it's just a couple sets of parallel lines. So for every bond that goes in between carbons, you should be able to find two hydrogens that are parallel to that bond, and then another bond on the other side of the ring that's also parallel. This kind of gets to the tricky part, so we'll get there. But if you look at mine, if you look kind of straight on like this out here is parallel with these middle two, and then it's parallel with the other end. And that's true as you turn it. So there's a lot of symmetry going on here. All right. So now let's try to draw this thing and try to get our model to match up with what we're drawing. So we'll start the way the book does it. You'll notice when I draw it, I do it a little bit differently. However it works for you is fine. But we'll stick with the book's method for now, just as a place to start. So the book says start with two parallel lines, one slightly offset from the other, like this. That's going to be our seat of our chair. And then the two sides are going to be the head and foot pieces. Yeah, exactly. Yeah, it's definitely a weird thing to think about. So let's try it again. Two parallel lines, offset a bit, and then that's our head, I guess, of the chair, and our foot. Let me show you the way that I would draw this, which is a little bit different. I actually start with the head or the foot and then go from there. So I draw this thing first, and then draw my parallel lines up this way, and then the other one. Okay. However you can draw a shape that kind of looks like that, it's fine. We'll talk about what makes it okay or not okay in a minute. This is this structure. So if you look at this, at an angle, those middle bonds should be those parallel lines that we just drew. And you should see this other thing coming up and this other thing going down without the hydrogens. What? We have to be able to draw these with all kinds of other stuff attached to them to learn a little bit about their structure and show what they're doing. So then we're also going to draw the flip version. Remember we were going like this, flipping it back and forth? So you flip it, and you have something a little bit different. You have it going the other way. So going the other way looks like this. Whoops, I have the same one again. Going the other way looks like this. You're going to have the other angle, like that. Sometimes they get a little skinny or not, as long as the angles are there. As long as you can clearly distinguish three sets of parallel lines. So you've got parallel lines here, here and here, and then here and here. And that represents the 6 carbons around this ring. There's no question that this is a weird thing that is difficult to get used to. But it's also not some kind of crazy, difficult concept. It's just a thing that you have to get used to drawing in a weird way. So what I recommend and what I actually did when I first learned this thing is I just took a pad of paper, and when I was watching TV or whatever, it doesn't take a lot of brain power, just keep trying to doodle these things out. Just draw them have a couple with you that look good, like that you traced off the book or something, and then just keep trying to repeat those shapes and just keep trying to draw it. And it'll come easier to some people than others. That's just how it goes.
You don't grade us for drawing, right?
What?
You don't grade us for drawing that?
Well, right. So there's, and we'll talk about this in a second. The point of this is to communicate the chemistry, to communicate what is happening chemically. So that means, no, it doesn't have to be perfect. It doesn't have to have the perfect alignment and the perfect angles. However, as we'll see, if it's too far off, you'll actually be drawing the wrong thing. And then it becomes wrong because it's no longer clear what you're talking about. And so we'll see some of those limits. All right, so the next step of this is to actually put the hydrogens on them as well. So give yourself some room and try to draw a pretty big, good one, if you can. And we're going to put in the hydrogen bonds on there. Mine always look a little worse on the screen here too, so it's, you can see there definitely is some room for error here. So we said a little while ago, there are two types of bonds in this molecule. There are the ones that go straight up or straight down, coming off the hydrogens, I mean. They're the ones coming straight off and straight down, straight up, straight down. And then there are the ones kind of going around the side. Ever see that? Grab your model, take a look at that. There's straight up, straight down, and there's off to the sides. The straight up, straight down ones are called axial. And they alternate around the ring. And the ones coming off the side are called equatorial, like the equator, going around the side. So we're going to do those first, because those are the hardest. The axial is less hard because it's just straight up or straight down. The equatorial, you have to get the angle right to show that it's going the right way. Now I'm going to show you how you do that. Start at an end, all right? And the equatorial or the sideways bond is always going to have the same angle as the bond that is 2 carbons away. So for an example, for this carbon, for the bond coming off of here, we're going to use this angle, which is also the same as this angle here. So we draw another line that is in line with those other two. So you see that? This one, and now this one are all parallel. That should be the same on your model as well. If you look at that end, I've got the wrong thing here. Here we go. If you look at the one coming off the end here, you should see that it is parallel with these 2 bonds right in the middle. And we're going to use that same pattern all the way around. So that means that this one coming off of here is going to take this angle, which should also be this angle. This one here takes these outside ones. This one here goes down and up and down. Okay? And those are all the equatorial bonds, the equatorial hydrogens coming off of this ring. Yeah. Yep. This is the bonds that come off of the ring, and they have to be in line with 2 of the bonds in the ring. So that one's going to line up with these 2, not the 2 that it's connected to, neither of those, but the other 2, the ones that it's not connected to. So you can look at this and say, all right, this is connected here and here. So it's not going to have either of those angles. It's going to take this angle over here. All right? This one doesn't take one of those. It takes that third angle. So there should only be 3 possible angles in this whole thing that these lines can be, including the ones in the structure itself, in the ring. For now, try to get a good drawing down. And again, it's in the book, so you can always look back at it. This is not something that you can just expect to be able to do right away. It's something you're going to have to practice. But I think it's something that you'll get. So then the final step to completely complete this is to put in the axial bonds, which are the ones going straight up and down. Okay. You'll notice that at each carbon, there's already an equatorial one either going up or going down. So the axial is going to complete the tetrahedron and go the opposite direction. So this one has an equatorial pointing up, so it's going to have an axial pointing down, and we just draw a line straight down. Now we can simply alternate up, down, up, down, up, down around the whole ring. So this one was down, so the one next to it's got to be up. Then the next one's down, and then up, and then down, and then up. Don't worry if they interfere with the other lines in there. Just try to get something down there.
This is how it's gonna be drawn every single time.
Yeah, either this or the other way. Right. So now that you've got something down, take your model and see if you can put it into that form and see how all those things that you just drew match up in the model. So can you find all the different bonds that you drew if you kind of look at a side perspective at your model? Do you see that? All right, once you have a sense of that, flip your model, and we're going to do the same thing the other way with the other conformation. Flipped conformation. Give myself a little more room here. The process, the procedure is exactly the same. We're going to just use the other conformation. So I'll just do it right here next to the other one. Oh, it's too small. Let me do it bigger here. That's not good. Hold on. I can only draw these things small. There we go. Okay, so once again, we're going to draw the equatorial bonds coming off around the side using the angles that are already in the ring to help us. It's going to look like this. And then we're going to finish up by adding the axial bonds going straight up or straight down on each carbon.
So, I'm a blue,
Mhm.
It goes up, is that equatorial line lining up with the bottom of the other group?
Say that again.
Okay,
So here,
okay, sorry on the left side.
here.
Okay, that, it goes like that. It goes, and then yeah, right there,
Yep.
that one lining up with the bottom of the other side. But it's,
So this lines up with this,
okay.
this, and this. Or it should. All four of those should have the same angle. Once you can draw these two more or less like that, you're done. That's the skill. That's what you have to be able to do. There are all kinds of different methods of doing this. You can look on YouTube. You can go back to this video and you can watch me draw them. People have all kinds of elaborate methods of coming up with grids of how to draw perfect ones. It doesn't matter that it's perfect. What matters is that it's clear which conformation you're drawing. Are you drawing this one or this one? And it's clear which of the substituents, whatever they are, hydrogen or whatever, is it clear that those things are either up or down and axial or equatorial? Right, so let me show you some bad examples, some examples that cross the line. Okay, I see some things like this. It's a chair, looks like a chair. That part is okay. But when you start drawing the lines on it, you get some weird stuff going on. So you get something like this. It's not really clear which of those bonds is equatorial and which one is axial, and which one is up and which one is down. You see that? How you can't really tell which one's pointing up or which one's pointing down? In fact, if this were drawn more correctly, then this one here should be more clearly up, but then it wouldn't be parallel with these anymore, so that wouldn't quite work. So this is an example of where it gets so far out of whack that it's no longer clear which is which. That's what I mean when I say that it doesn't have to be perfect, but it has to be clear enough which thing is going where. Otherwise, I'm not sure that you are seeing it properly. Okay. Let's stop there and take a little break. We'll come back and we'll finish up with putting substituents on these. That is what happens when we actually connect things and watch them flip back and forth. Just try to clear your head a little bit and we'll go on. Yes. So this one's going to go a little out of whack. This one looks really good. But this one's a little bit. Oh, I see. Okay. So the yeah.
Can't figure it out.
So the issue here is that you're drawing these two lines at the same angle as these two, and you're only flipping the edges. But if you look at this, what really happens is
And
the
see, I
middle two
can't
lines.
tell from that.
So if you look at the middle two like that, and that's the one coming up here, and then right there. And then if these things flip, the one coming up, these middle two go up. So they're now opposite. Yeah. So if you look back here, when you draw one conformation, you're drawing two lines going this way. When you draw the other one, they have to go that way. Then I think it'll be okay.
Yeah.
So now these ends should fall more nicely in place. Right, not quite at such an extreme angle. You will get it right here. Then you should be able to get those more in there. Let me stop this.